So mechanisms of temperature regulation. So this is how your body regulates your temperature. You can vary the rate of heat production, and this is your metabolism. So in a cold environment, you're going to increase that metabolism by shivering, and this will keep your core temperature elevated. But also in a hot environment, then you're going to reduce possibly the thyroid hormone, lower your metabolic activity, and lower your heat production so that you don't overheat. You can also vary the rate of heat transfer between the surface and the environment. So your surface being the skin and the environment. If you push blood to the surface in a hot day, then you will tend to lose heat. But then also if you pull heat away, pull blood away, then your skin will be lowered because it'll more be the same temperature as the environment, and so you won't lose as much heat. And then you can vary the rate of heat transfer between the core and the surface, and this is changing the circulation either closer to the skin so you lose more heat, or further away so you have this insulating layer that prevents heat loss. And these are the three main ways that you will regulate your heat. So when we're talking about raising your metabolic rate or altering your metabolic rate, which is the first way we talked about just then, you have these different exercises. So sleeping, as I talked about, very low metabolic activity, 35 kilocalories per meter squared per hour. And then on the other end of it, you've got running, which is about 600. And in between, we have various levels of swimming and bicycling, lumbering, if you're so inclined to do that, standing around. So at the moment, I'm burning about 90 kilocalories because I'm not just standing, I'm talking. But shivering to about 250. So you have these different ways of elevating your metabolic rate that allows you to then modulate your core temperature. And then on to surface heat exchange. So this is between your skin and the environment. So conduction, convection and radiation can either cause the body to lose heat to the environment or gain heat to the environment, and it's all dependent on which is hotter. If it's hotter outside, you're going to be gaining heat. If you're hotter than the environment, you're going to lose heat, and this is shown here. So if the atmospheric temperature is greater than your skin, you're going to gain heat. However, if the atmosphere is less, then you're going to have heat loss, and if it's much less, you'll have excessive heat loss. And the only way to respond when there is an excessive heat loss is to lower your skin temperature so that the skin temperature is as close to the atmospheric as possible, and so it reduces heat loss. And so when your skin is cold and the atmosphere is cold, there's really not much heat being passed. And so this is then affected, as I'll go into in more detail in a second, by withdrawing blood away from the skin and letting the skin cool. The skin is increased by increasing blood flow to the skin, and TS is decreased by decreasing the blood flow to the skin. That's kind of what I talked about. It starts here about increasing blood flow to the skin is going to warm your skin, and then depending on what the atmospheric temperature, that will increase heat loss, and then vice versa. If you pull blood away from the skin, then you're going to reduce that heat loss. When the atmosphere is greater in temperature than your skin, the only way to lose heat is through evaporation. Now, evaporation will still occur, especially if it's hot, and as that water evaporates, it will take heat with it, even though the atmosphere is hotter than your skin. It'll just take energy away with it. And And in this case, the body only gains heat from the environment by conduction, convection and radiation. So your sweat is evaporating off and you're losing heat, but you're also gaining heat as well because of the hot air that swirls around you and the infrared that comes through into your body. Sweat is secreted by eccrine and apocrine glands. Only eccrine glands are involved in thermoregulatory response. So this is controlled by the sympathetic and cholinergic systems. And then the rate of sweat evaporation depends on the humidity and wind velocity. So if it's very humid, you're just going to get wet and it's not going to sweat much, you're not going to lose much heat. But if it's kind of humid and windy, then it is going to kind of pull some air off you. But if it's dry and windy and hot, that sweat's not going to stay in your skin very much and you lose a lot of heat like that. And then insensible evaporation is unregulated and reasonably constant. And this is just the fact that you're always secreting some kind of fluid out of glands and it just dissipates into the air. And it will vary as well with humidity and the heat of the environment, but generally it's about 25 to 30 mils per hour. Okay, so transfer of heat from core to the surface. Now this is all about changing the circulation of the body. So conduction, simple cell to cell transfer of heat, normally much less important than circulation, but it does determine the minimum amount of heat transfer in extreme cold where there is extensive peripheral vasoconstriction. Now what this means is if you pull all the blood out of the shell, pull it away and you have very little blood flow through that, that's about as low as the thermal conductivity of your body will get. And so when it's really cold and you want to conserve heat, all that blood comes away from your fingers and toes. You know, you can feel it when you're really cold, and what you're left with is the basal level of thermal conductivity. But the circulation then is the transport of heat by the circulatory system that's needed to perfuse the body with oxygen, and this will deal with varying levels of heat production. It'll overcome the insulating properties of your fat, and it'll counter non-uniformity of heat production within the body. Different organs produce different amounts of heat because they have different metabolic rates, and so this circulation will dissipate the heat from different organs and keep your core at a more constant temperature. So the cutaneous circulation, it supplies the metabolic needs of the skin, which is normally over-perfused. More circulation than oxygen is required. Warm blood to the skin, this cools the blood in the body because you've now moved the blood outwards. The thermal conductivity of your shell is greater and heat will flow out faster. Keeping the blood out of the skin conserves heat. You just talked about it. When you pull blood away, then your thermal conductivity, the thermal coefficient of your shell is lower, and this will conserve heat because it will be slower to leave the body. Blood flow to the entire skin can be varied by about 100 mils per minute or less, and as much as 4,000 mils per minute in a warm environment. So you have a great scale of change so that you can really respond to the environment. It might be slightly cold, so you'll only pull a bit of blood away, or it might be really cold and you pull it all away and you have about 100 mils per minute in your periphery. Or it could be really hot and all the blood will be flowing, be all red and losing lots of heat. Transferring blood to the skin changes the thermal conductivity of skin. I've said it several times, and that's because it is worth repeating. And the effective thermal conductivity of the periphery or the body is defined as the rate of heat exchange between the core and the surface is equal to the coefficient, the effective thermal conductivity coefficient, times the driving force, which is the difference in temperature between the skin and the core. And so the speed that you will lose heat is dependent on the amount of circulation that's going through it and the difference in temperature. Okay, blood flow to the skin can be varied by vasodilation and constriction, and this happens through venous plexus, arteriovenous shunts, and anastomosis. Okay, so now we're getting into the specifics of how the body regulates this circulation. The venous plexus and arteriovenous shunts. And so the body can move things from the periphery or inside by opening and closing these. And dilation of the shunts causes warm arterial blood to be poured directly into the venous plexus and the dermis and epidermis. So when you're warm, these shunts open and the blood flows to the surface, and you lose heat to the environment to try and cool your core down. The short muscular vessels of the AV shunts are heavily innervated by the sympathetic nerve fibers. So it's a sympathetic system that's going to be working these shunts. A vasoconstriction of the arterioles, meta-arterioles and AV shunts are under control of sympathetic center located in the posterior hypothalamus. The hypothalamus is the king of your temperature regulation. You do have reflexes around, but it's mainly the hypothalamus that dominates. So your continuous blood vessels also respond directly to heating, so you lead to vasodilation. So in result, you have local responses, but they are in part dependent on hypothalamic control, and control of the continuous circulation is then an integration of the CNS, spinal cord, reflexes and local control, but the hypothalamic control usually dominates. Okay, this graph shows you how the conductance, thermal conductivity of your periphery changes as you raise core temperature. So you have the tympanic temperature here of the core and the conductance, and as you get up to about 36.9, 37, the thermal conductivity rapidly increases with the temperature as the blood moves into the periphery, and that blood flow then really increases the thermal conductivity of the skin. Okay, countercurrent heat exchange mechanism. So this is kind of another way that your body can regulate your temperature, and this is due now to sort of deeper veins, the deeper system. In response to cold, venous blood from the extremities is shifted to superficial and deeper veins called venous commentans. And these are deeper veins that kind of wrap around your arteries, and they will bring the blood inside, and this does two things. The blood in these deeper veins is warmed by the adjacent arteries. So these veins have been out in the periphery, it's got cold, it's coming back into the core, and that's bad. So before it gets to the core, it runs down the length of the arteries and warms up a bit, so you don't lose so much heat because the returning blood is warmed, and at the same time arterial blood is cooled on the way to the surface. So as the warm blood goes out, it gets colder, and that heat is brought back in through the vena commentans, and therefore you limit the amount of heat loss. And so the venous blood is warmed while returning to the core. And this is shown here. So on the right we have how it is in a warm environment. You have arterial blood flowing down, and it's at 37 degrees, and it's nice and warm outside, so the blood is pumped back up the veins, and it doesn't really lose that much heat because it's nice and warm, and so you have separation between the circulations. But here in the center, now it's cold. The arterial blood is flowing down, and you can see these venous commentans that spirals around the arteries, and so the warm blood coming down is cooled by this cold blood coming back up, and this cold blood is warmed by the warm blood coming down. And so you, rather than lose that heat to the environment, it's conserved and it's brought back into the center of the body through these venae comitales.